Okay, so current flow in a PN junction will conclude our discussion today. So we said that current can be computed at any particular place in the PN junction, and so we could write, just to quickly, we could write, for example, J equal to JPXN plus JNXN, and we said that JNXN, we could, this was an approximation, JNXN equal to Jn minus XP. Whatever is the electron current that enters at Xn is equal to Jn minus XP. If we want to be exact, we should write as some recombination current Gr, because all the current that enters, all the electrons that enter here, they don't come out on the other side because they undergo recombination. And therefore, JNXN is larger than JNXP by an amount which is equal to the recombination current. Where is this recombination current? In the depletion region. We also call it the SCR recombination, space charge recombination. It's SCR or depletion region here. Depletion region recombination. Right? So in this here. And the assumption that we make is that we consider JR, assumption JR much less than, let's say, Jn minus XP, and therefore we write Jn Xn equal to Jn minus XP. And therefore we are able to write J equal to JP at Xn plus Jn at minus XP. We're able to write the total current in terms of these minority carrier currents here. Minority carrier currents. We are able to write them in terms of minority carrier currents, and we had also seen earlier that minority currents JPXN, minority carrier currents are, this is also an approximation, minority carrier current is diffusive. So Jp is minus Q dP del P by del X at Xn. And similarly, Jn at minus Xp equal to Q dN del N by del X at minus Xp. They're diffusive current. And therefore, the problem becomes how to determine these two components. What are these two components here? What is this del P by del X and what is del N by del X? And we had also seen that if I look at my PN junction, if I were to look at my PN junction and draw my excess electron hole density, so excess hole density goes like this, delta Px, and excess electron density goes like this here, delta Nx, the minority carrier density. And we had also solved the way you determine delta Px. The way you determine delta Px is you take del P by del T, your continuity equation, minus 1 over Q del Jp by del X. There's no recombination. If there is a Gp minus Rp. And Rp we model it as delta P by tau P. And if there is a light shining, then you'll put G there. Then you get a solar cell kind of an operation. If there is no light which is shining, then you put G equal to 0, right? So you put G equal to 0. And we are talking about steady state, so you put this equal to 0. And we already have expression for how Jp goes in N-type region. Jp in general is diffusive. So you do that, and you solve a second order differential equation, which we have done that, and you're able to get what is the variation of delta Px. And we said delta Px will go as delta P Xn multiplied by e to the power minus, I've just shifted the origin, e to the power x minus xn by Lp. That's how it would diffuse if this region is very thick, if L is much larger than Lp. If that is true, then you can write it in this particular form. Similarly, delta Nx you can write as delta N minus xp multiplied by e to the power plus x x plus xp by x plus xp by ln. And here also we are assuming that this region is very, very large. If it's not very, very large, we'll see in a minute how to do that. So we know these expressions here. We have done that continuity equation solution. So then if that is there, then it's easy to calculate what is this derivative. The derivative simply becomes, if delta p, for example, let's take this particular term. The derivative, then we can write this as q dn del n by del x. So, this is, let's write this particular part here, del p by del x here using this. So this becomes simply equal to q dp delta p xn by lp. Simple differential of delta px by this thing taken at x equal to xn. It becomes q dp delta p xn by lp, and this similarly becomes q dn by ln delta n at minus xp. So this becomes this component here. Right? So this becomes this component here. So our total current J will be the sum of these two components here. Q dp by lp delta pxn plus q dn by ln delta n xp. So the whole problem then turns out to be, what is this? This is where we were in the last lecture. What is this delta pxn? Or what is this delta n xp? We have to relate it to voltage. If we can relate it to voltage, we have an expression of J versus, we will get J as a function of voltage. Okay, so this is where we were till the last lecture. So let's look at how do we compute delta pxn and delta nxp. So if I do this, then the same expression holds because of a similar kind of a argument. The same thing holds for the other side also. Okay. So please note the assumptions that we have already made. The assumption, one assumption that you can see here, if I can just circle an assumption, there is one assumption here. You are neglecting recombination in the depletion region. There's another assumption is here. Here. You're assuming that the minority carrier current is diffusive. We know that there will be a little bit of electric field. We had discussed that. But the electric field's effect on minority carrier current is negligible. That's the other assumption that you see here. The third assumption, some of the assumptions, as we have said, are sort of buried. The third assumption is we are assuming that the diode, if I can call it assumption number one, whichever one, I mean assumption number two, there's an assumption number three. We are saying that the diode is very thick. The length of the diode is much, much larger than LP, because if it is not, then this equation will not be valid. These equations will not be valid. We'll see today what happens if the diode length is not very, very this thing here. We are also assuming, if you look at it, we are also assuming that there is no generation rate. There is no generation. In the sense there is no optical generation, no external stimulus. We are assuming G equal to 0. Right? So we have A3, you can say A4, assumption 4. So various assumptions go in the final calculation. So let's look at then what is this delta Px. So this is the behavior that we have. Delta Px goes like this. So total hole density here in this region will be equal to the background hole density plus delta P. Anywhere inside the N region would be P0, equilibrium hole density, plus the excess hole density because of injection. N dash will be equal to the background electron density, and because the region is quasi-neutral, so delta P is equal to delta N. So that is there here. And so one is also making an assumption. For a moment, let's wait for this particular assumption here. So the issue is, so this is what we have. We have excess hole density, we have excess electron density. All right. Let's look at the band diagram. This is the band diagram in equilibrium. Okay, so note, why are we going to the band diagram? Because we have to relate P dash and N dash and all of that to voltage, because the voltage so far has been missing from our discussion. We have written expression for current and all that. So finally, you must see here that when I want delta Pxn and delta Nxp, this is where the voltage will come into picture. So I have to relate this to how does delta Pxn, how does it change with voltage? Right? How does it change with voltage? We want this relationship. That's why, and when you want a relationship with voltage, the band diagrams are helpful, because band diagram basically shows the variation of bands, and bands are nothing but variation of voltage. Okay, so that's why we are looking at it, and let's see, this is at equilibrium. Now, this is at when I forward bias the, note that this is N region, and this is P region. And N region, I keep it to ground, and P region, I apply a positive bias. So when I apply a positive bias, what happens is my bands go down. My bands go down here. And we know that the net voltage across the junction goes VBI minus V, whatever is the voltage that you apply here. And note that what we are saying is far away, see the argument far away from the junction. We are not just far away. In fact, we are saying at the contact. We are assuming ideal contact. Okay, so this is the assumption that comes from ideal contact. If I didn't have ideal contact, so ideal contact means it's like an ideal sink. It's like an ideal sink. So ideal contact, we say always you have equilibrium condition prevailing. So at equilibrium, of course, ideal contact, it is at equilibrium. When you apply a voltage, the ideal contact is not affected by applying voltage, by currents flowing. Okay, so in that sense, we are saying equilibrium condition, obviously it's not strictly in equilibrium, but equilibrium like condition will always be there at the ideal contact. So we are assuming ideal contacts, and that's why we are assuming that EFN equal to EFP, and it stays at the same place with respect to Fermi level. EF right there at that particular point is exactly the same place where the Fermi level is with respect to, you know, whatever was the gap between EF and EC here, the same is the gap between EF and EC here. EFN equal to EFP. Equilibrium means you don't have separate quasi-Fermi levels for electrons and holes. So EFN equal to EFP. So it stays there. Similarly, at the other side, it also stays there, at the contact only. Okay, at the contact only, it stays at that particular point. Now, what is this dotted line? The dotted line was equilibrium Fermi position. Okay, all right. So this is there, and so the whole band diagram moves down. EFN, what we could do is, this is slightly redrawn. What we can do is, you know, you could say my EFN equal to EFP, if I were to draw in equilibrium, EFN equal to EFP remains here at the same place, right? Because this is ground and at the same place. And EFN and EFP would, you know, would stay at the same place with respect to EV somewhere, let's say somewhere here, you know, whatever was the gap here. So what you find is that there is the voltage difference shows up in this. This is the voltage difference that we are drawing here. This is equal to QV. Just because on one side the bands remain the same, on the other side the bands shift down. And we are saying it's equilibrium condition here. So the Fermi energy here also moves down, right? So we say EFN equal to EFP here also. But it stays next to its band. And similarly, EFN equal to EFP, it stays close to its band, wherever it was with respect to it. And therefore, because bands on one side has moved down, so there's a splitting of the Fermi energy that you see. If I were to draw a line here and draw a line here, you see that there is QV here. Okay? So same way you can draw in this particular band diagram, what we have said is that the P side remains the same, N side if you apply a negative a positive voltage here. So here. Oh, sorry, N side you have applied a negative voltage, so it moves up here. So that's why we have shown this moving up by an amount equal to Q times V here. Okay, so either way, either P side moving down by QV or N side moving up by QV is the same thing here. Okay. So you're saying that EF here and EF here are going to be different. The two are going to be different here. And how different? Well, there is a gap between them by an amount equal to Q times V. Okay, so we know at the context because we have defined the context to be ideal. And so we know where the Fermi levels are at the context, ideal context. What happens to the Fermi energy as Fermi levels as we move further down? Okay. Now, note that we have written these expressions earlier, P equal to Ni EI minus EFP by KT. We've also shown that the whole current can be written as gradient of whole quasi-Fermi level. We've also shown that similarly, please realize that I can also write Jn equal to n mu n del EFN by del x. We can also write this. So the gradient in quasi-Fermi level is related to the electron current. So the idea now is, if you think about this region here, so here is, so EFN equal to EFP, fine, but let's focus on EFN. Now as it starts from the ideal contact, does it remain, what happens to EFN? I'm drawing EFN, what happens to it? Does it remain flat? Well, obviously not. Why? Because there's an electron current, there's a gradient, right? There's a gradient, but what does the gradient depend on? Del EFN by del Fx, there's a Jn, and there is this n here. And what is n in this particular region? N equal to Nd, roughly, right? Because it's an n-type semiconductor. So what happens is, this n is pretty large, and this is Nd is fairly large. So what happens is, yes, there's a gradient, but it almost remains, the gradient is small. So what we say is, well, it remains almost the same till this particular point, till the edge. Remember? Edge of the depletion region. Once you go inside the depletion region, what happens to n? N starts to sharply decrease. So I cannot now make that assumption that this is flat. This is approximately flat till here, but after that, well, it's going to go. It's going to go. Right? Because n is sharply reducing. Note that, look at this expression here. Jn is also changing, but not changing that much. But look at n. N sharply begins to reduce, and therefore the gradient becomes significant. On the other hand, same way if I look at EFP, EFP will remain constant. EFP will remain constant. EFP will remain constant here because it's p-type, and will remain constant till about this, till you enter the depletion region. And once you enter the depletion region, EFP would also start to change. That's the behavior that we are saying you're getting. Okay? EFP would also start to, but the other thing is, so although it will start to change, but remember how thin is the depletion region. Depletion region is actually quite thin, maybe hundreds of angstrom. And that also we are saying we are forward biasing it. So forward bias, the depletion region even becomes smaller. So it's a reasonable assumption that even though gradient may be there, I could say the following. I could say that this is almost constant till here. Because the depletion region is very narrow. Yes, n is actually going down, but depletion region is very narrow. Remember, n is continuously going down. And similarly, I could say this is also, depletion region is very narrow, and this is also constant in that. Now what happens is, now in this, it goes like this here. It starts to decrease. And this one will eventually, because note that they have to return back. Eventually equilibrium has to be there. So they have to return back to this at the other end here. So the two, EFN and EFP, have to merge together. So look at the behavior of EFN and EFP. Understand why we are saying each one of those things. Is flat, EFN is flat till here, because we look at this expression, we say n is pretty large, n equal to Nd. So it's approximately constant till this particular point. Yes, n is decreasing, but this region is also very narrow, and we keep it flat here. And then after that, we know that n has to, the quasi-Fermi level has to reduce and eventually merge with the EFP, because equilibrium prevails at the contact here. EFN equal to EFP. Same behavior occurs at this particular point here. Okay? So this is the behavior of EFN and EFP in a PN junction. How the quasi-Fermi levels go. now this makes it interesting because now what you see here with these assumptions, what you see here is that this difference between these two is also equal to QE. This difference between the two is also equal to QE. This difference is QE. So this is also equal to QE. So what we are saying is at the edge of the depletion region, the electron quasi-Fermi level and hole quasi-Fermi level are not the same. They're split from each other. And the splitting is equal to QE. Same way here also. This is also QE. But after this, once you enter here, of course, it keeps on reducing and becomes negligible and becomes negligible. Okay, so there is an assumption here also involved. Okay, note that the assumption is there because, of course, there is a gradient here. Of course, there's a gradient here. But we are neglecting that gradient. We are neglecting, and you will see what that neglecting that gradient, what does it really mean? So realize, so if there were a gradient, what do you think would have been the difference between here and here? If I had taken, let's say by some means I could do exact analysis and the whole electron quasi-Fermi level has a gradient, what would this difference be equal to? Will it still be QE? Huh? Less than QE? Similarly, if I look at it here, it would also be less than QE because of all that. So what you're saying is there is a gradient in quasi-Fermi level which would cause these differences to be less than QE. But we are saying, well, that gradient is very, very small and is almost equal to QE. Okay? It's almost equal to QE. So we'll come back to that. So this voltage V, so in a way, this voltage V, okay, all right. So let's go forward. So this is there. The same behavior, we're plotting it here. So we know these two equations, n equal to ni exponent EFn minus EI by KT, P equal to ni exponent EI minus EF by KT here. Both these expressions we have seen earlier. If we multiply them together, we get P into n is ni squared exponent EFn minus EFP by KT. Now, our interest is at the edge of the depletion region. Apply this equation here at the edge of the depletion region. So you get P into n is ni squared exponent QV by KT. Because the gap between at the edges at this particular point is equal to V here. So you get P into n is ni squared exponent QV by KT. Note that in the entire depletion region, the product of P and n is ni squared exponent QV by KT. Here the voltage drop is the difference is QV by KT. So everywhere it is, PN product is at the edge of the depletion region and inside the depletion region. Both at the edge and inside the depletion region is ni square exponent QV by KT. Next, what we do is same thing. We write P equal to ni square over Nd, the background hole concentration plus the excess hole concentration here. N we write as Nd plus delta P. Delta P because N should have been written delta N, but we know it's quasi-neutral, so delta N equal to delta P. So we write it here, and we multiply it together. Nd plus delta P. Now note that, you can do an exact analysis. You can write Nd plus delta P, and you could write delta P plus Ni squared over Nd. But if you do a little bit of calculation, you find, let's say this is 10 to the power 3, and for any significant current, you will find that this is maybe 10 to the power 11, 12, or something like that. Okay, so this is much higher, and that's why we have sort of neglected this here. So we've written P equal to Nd plus delta P into delta P is equal to P into N. All right, here Ni square exponent QV by KT. So what is the assumption here? Well, you're looking at a case where you have applied significant voltage. Even if you apply 0.1 volt or 0.2 volt, we're talking about PN junction. 0.1 and 0.2, you can do the calculation later on, and you can see even if you apply 0.1, you will find that this is much larger than Ni square over Nd. Okay, so this is fine. I mean, there is no issue of saying P equal to delta P. P equal to delta P. I mean, it's there right from maybe 50 millivolts or 100 millivolts onwards. Okay. So with that, you come to this expression here. Nd plus delta Pxn into delta Pxn is Ni square exponent QV. At this point, you make another assumption, which is low level injection approximation. The injected hole density is much, much smaller than the background doping. All right, so we make this particular assumption. So what we are saying is, in this one, we can approximate it as ND. Okay, so you have injected, we are talking about N region. Of course, there are electrons which are equal to ND. You have injected holes into it, but we are saying the amount of injection is, number of holes that you have injected is much smaller than the doping. So with that in mind, you obtain ND into delta Pxn, we should put here, Ni square exponent QV by KT, and you obtain delta Pxn is Ni square over Nd exponent QV by KT. And same way, you will obtain delta N minus Xp equal to Ni square over Na exponent QV by KT. You obtain this expression, excess hole density. And that's what I said, you can easily verify. This is delta Pxn, put a value of forward bias, maybe put 0.1. If you put 0.1, you get exponent e to the power 0.1 by 0.026, and you can see this is a large number compared to 1. And therefore, what we said was you can easily neglect here, Ni square over Nd. You can easily neglect that, okay? All right, so with that we have obtained what is the hole density at the edge of the depletion region here, and what is the hole density at the edge of this depletion region. We have obtained both these quantities here, right? And with that, then we can obtain the final expression, okay? So this is where we are. Delta Pxn is Ni square over Nd exponent QV by KT. Delta N Xp is Ni square over Na exponent QV by KT, right? So these are things that we have gone before. So we have discussed where to calculate all of that there. Yes.
So can we qualitatively obtain the behavior of electron polyformy level in the P region? You have shown it decreasing linearly.
No, not linearly. Anything in band diagram is qualitative. Don't go by how we draw the band diagram and infer that it's a linear or a quadratic or whatever. Sure, we will see. Okay. So finally, I'm just skipping it. So finally, what we get is we have done all of this here. These are, you can see the notes later on. We've done all of this part here, right? So finally, we can write down each one of those. We had written Q dP by Lp delta Pxn, right? So we write this here. At this particular point, Ni square over Nd exponent QV by KT minus 1. And similarly, we write Jn minus Xp as this particular expression. And we add the two, Jpxn and Jn minus Xp, and we get the well-known diode equation. Q dP by Lp Ni square over Nd, Dn by Ln Ni square over Na exponent QV by KT minus 1. Okay. Lots of assumptions went into derivation of this particular equation here. Okay. So if this is a summary, see if it makes sense here. You were asking about flat EFN here and how this goes here, and flat EFP here and how it goes here. How to calculate those things will come in a minute. So we have this. So Pn into Ni square exponent QV by KT. Now I'm calling this assumption that this flat till at this particular point here, I'm calling this assumption as negligible voltage drop in the bulk. Because note that what is the consequence? We just saw that if this were not flat, what would you have gotten? The drop from here to here would have been less than the applied voltage here. So where did the rest of the voltage go? The rest of the voltage, there's a gradient, so it got dropped here. So the voltage across the junction, if you're assuming negligible voltage drop in the bulk, which means that the gradient is negligible here. And so all the voltage that you applied appeared across the junction here. So that's that particular assumption which allows us to write this here. The next one is low level injection we just saw, which allows us to write delta Pxn as Ni square over Nd exponent QV by Kt here in this form. Minority carrier current is primarily diffusive. That assumption we've been making because everything is in terms of hole current here and electron current here, minority carrier currents, and we are writing them as diffusive. And we are assuming very thick N and P region, so we've been able to write it like this, exponent minus x minus here, and this assumption. We've also said, well, we have said that the current, for example, if you look at the whole current here, the whole current here and the whole current here, we have assumed to be the same by neglecting recombination. Similarly, the electron current here and the electron current here, we have same. So we are neglecting recombination within the depletion region. So these are all the assumptions that go in defining what the current is. So, you know, whenever you are doing semiconductor device and you're deriving an analytical expression, you have to keep into mind all the assumptions because they define the range of validity. For example, assumption number 1. Well, assumption number 1 is saying there is a boundary now. If you cross that particular boundary, your assumption will be invalid. So I'm drawing a boundary like this here and saying above the boundary, assumption 1 is valid. Below the boundary, assumption 1 is invalid. Okay? Then I'm drawing another assumption. You saw all the assumptions, 5, 6 assumptions that we have made. I'm saying outside here, the assumption is invalid. Inside here, the assumption is valid. Assumption number 3. Above, invalid. Inside, valid. Assumption number 4. Here, invalid. Here, valid. So what happens is all these assumptions are finally defining a region. Finally defining a region where your equation is valid. Which equation are we talking about? The ideal diode equation. J equal to, this is what we have derived. E to the power QV by KT minus 1. Let's see if you can list some of the assumptions. Assumption 1. Huh? Okay, so you can say it in whichever order for a moment, but this is important because it's equally important to know how to derive this J equal to Js and what are the assumptions in which you have, because that defines the region in which is valid. Assumption 1? Which one? Depletion width. No, a depletion width. Okay, so let's say, he's saying negligible recombination. Negligible recombination in depletion region. Okay. Actually, there are more than 4. Another one?
Very thick PN.
Huh?
Very thick PN.
Thick PN engine. Thick PNN region. Then?
Electric field 0 in the bulk.
Huh?
Electric field is 0.
Okay, so what it's saying is negligible drop in the bulk. Negligible drop in the bulk. Or anything else? Minority carrier current is diffusive, is also low level injection. Both low level injection. Low level injection. So you can see all these assumptions will define a range within which your ideal equation would be valid. Now obviously there are some things which are very easy to see. Where would this assumption be violated? Low level injection. What does it mean? Delta P, injected delta P, suppose I take N region, delta P is much less than ND. Where do you think it will get violated? When you go to higher voltage. Because delta P keeps on increasing as E to the power QV by KT. So if you keep on increasing V, a stage will come when delta P will start becoming comparable with ND. So this assumption will break. Not only will this assumption break, in fact, as you go to higher biases, this will, so higher bias, if I write, higher bias, at higher bias, this assumption will break. At higher bias, this assumption will break. At higher bias, these two, negligible drop in the bulk and low level injection, both of them will break down. And I have to show you, this is a structural property, thick or N and all that, so it's nothing to do with bias. At low bias, I have to show you that, at low bias, this is the one which breaks down. At very low bias. This assumption breaks down. Negligible recombination within the depletion region. This breaks down. So what happens is, your diode expression that you just derived is valid neither at very low voltages, neither at very high voltages. It's valid in the middle. Okay, let me show you an example. This is the ideal plot. This is the real plot of a PN junction. Okay, this is from simulation, no assumptions made in this particular plot here. No assumptions made. All right, no that minority carrier is diffusive, drop in the bulk, nothing. Okay, now look at these characteristics here and see and look at your equation. Your equation was J equal to Js e to the power qv by kt minus 1. You can see that the equation is getting violated at both places, lower bias and higher bias here. See, if I draw this line here, straight line, this is this equation that you just derived. This equation is at higher biases it breaks down, at lower biases also it breaks down. Note that what do I mean by lower bias? You can see around 0.4 or so. At 0.4 or so it breaks down. And what do I mean by higher biases? Maybe around 0.7, 0.75 it breaks down. The current starts departing from these. So those assumptions are breaking down that I said. Here is breaking down mainly because of recombination. There is recombination occurring in the depletion region. That's the source of this assumption breaking down. And the drops are occurring at this particular case here. Okay. All right. Several things that are there here. Okay, so let's look at a concrete example here. So Na is 5 times 10 per 16, Nd is 5 times 16. So this is a region which is for making a contact to the P side. This is a region for making a contact. And note that these are all in microns. So one has taken a pretty thick P region and a pretty thick N region here. Now, why are we saying it's pretty thick? Well, if you take dn of 20, typical value, dp of around 10, and tau n and tau p of 0.1 microsecond. So the first thing that you should do is, when you're given dn and dp, you should calculate what is lp. Lp is square root dp tau p, and ln is square root dn tau n. And you should calculate these values and see whether this region is pretty thick or not. Pretty thick means it should be much, much larger than that. Okay. So what I'm doing is, look at this one here. I'm applying a voltage of 0.6. Okay, 0.6 volt. And I'm doing all the calculation for 0.6 volt here. Or a symmetric junction, 5 times 16, 5 times 16, silicon, dn, dp, everything is given to you. Okay. So this is the current. ln is 14 micron, right? LP is 10 micron. And remember, what was the thickness of P and N region? 50 micron. So 50 micron is just crossing this. 14 into 3 is 42. So it's larger than 3 times that, and it's larger than this. So this equation that we have written is valid as far as thick PN junction is concerned. Okay. These are the assumptions that have negligible voltage drop, low level injection, minority carrier diffusion, negligible recombination, all that is there. So thick PNN region is valid. All right, so I calculate J. I put in all the values here. I get J 0.185 ampere per centimeter square. Okay, so we draw this. Delta Pxn, we can calculate Ni square over Nd. Everything is being done for 0.6 volt. So this turns out to be, if I plug in the value, 4.7 into 10 power 13. Much more smaller than Nd. Nd is 5 times 16. Okay. Low level injection is fine. Assumption is fine. So note that I've applied this equation and calculated a current, but my current will be right only if the assumptions are right. So I'm now going back and checking, is each one of my assumptions valid or not? Okay. So this is valid. So this is JP and this is JM. Correct? JP and JM. I can calculate each one of those components. Note that I can calculate dP by LP Ni square over Nd exponent QV by KT minus 1. So that gives me the whole current, 0.075. And I can calculate dN by Ln Ni square over Na, that gives me this current. So that's 0.109. Is current in PN junction diode a minority carrier current? Well, I can calculate Jn and I can calculate Jp because I know the total current, right? Total current is there. I can calculate these also. So N region, if I look at N region, Gn is 0.109. Gn is made up of these two terms. Remember, only whole current is diffusive. Gn is made up of these two terms. Rho is fine. Del N by del X is del P by del X. Just follow the arguments. Gn diffusion is Q dN del N by del X is equal to minus dN by dP minus Q dP del P by del X is equal to minus 0.158. Gn diffusion is minus. Gn drift is 0.267. Because we know the total Gn, we have calculated Gn diffusion, so we know Gn 0.267. So find Jp is 0.075, Gn is so much. I've calculated Gn diffusion and Gn drift. The largest current component in all of this is Gn drift, right? It's neither diffusive, neither minority carrier current. But we know why we are calling it minority carrier current. Now, once you have Gn drift, note that once you have Gn drift, 0.267, I can calculate Qn, mu, and F. N is about Nd. I can calculate what is the field right at the edge of the depletion region. There is a field there. F, I can calculate, is 0.042 volts per centimeter. Extremely small field, but it does make a difference. So now this field is there. Now with this field, you can calculate a whole drift current also. So Jp drift will be Qp mu p F. P we already know at the edge of the depletion region. So I can calculate this. Delta Pxn is Ni square over Nd 4.7 10 13. We can calculate this current. Look at that, 1.2 into 10 power minus 4. This is the Jp drift. What was this? Jp diffusion. You can clearly see this is much smaller than this. So I'm okay in neglecting that. Okay. Jp diffusion by Jp drift is equal to 624. Diffusion current is larger than drift current by 600 times. So we are okay. That's why we are neglecting it. Now, if this is Fxn is 0.042, right? 0.042. Now, I can calculate how much is the voltage drop from here till here at this point. Now, how do you calculate that? Well, note this expression. Gn drift is Qn mu n into F and Q dn mu n F here. Can you calculate, I will leave it as a homework problem, can you calculate F everywhere inside the device? Is it possible for you to calculate F everywhere in the device? F everywhere in the device. Note that this is Jp here. Can you calculate Jp everywhere in the device here? How does Jp go? Exponentially decreasing. So Jp goes as whatever is at this particular point, e to the power minus x minus xn by Lp. You can calculate it everywhere, how it is decreasing. So if you know Jp everywhere, do you know Jn everywhere? Because Jp plus Jn is constant. So you know Jn everywhere. How does Jn diffusion go? Note that Jn diffusion and Jp diffusion are related together. So you can calculate Jp diffusion and you can calculate then Jn drift. And from there you can calculate F. You can calculate F everywhere. And if you integrate F, you will get total voltage drop from here to here. Total voltage drop. But suppose you have, we have F of a field of 0.042 and you assume that for a moment the field is uniform everywhere and you multiply it by the thickness of this one, you'll find there's only 0.2 millivolt drop. So you apply 0.6, there is a 0.2 millivolt drop here from here to here. So almost everything is going here. Similarly, there will be a 0.2 millivolt drop or something like that here. So it's a very small drop that is occurring. So the whole voltage appears across the junction. So we are fine in terms of all these assumptions that you see here. Low level injection, diffusive, negligible voltage drop, all of that is fine. Negligible recombination within depletion region? Well, here. This is how our behavior is. Note that JP is decreasing, JN is increasing, and JP we have assumed to be the same across the junction. No recombination. If there were a recombination, JP would have dropped. Similarly, JN is here, JN would have dropped, but we have made a line flat. No recombination. So this is how it goes here. But in actual practice, so all this is current is determined by minority carriers. We have seen all of this here. I'll skip some of these things. Recombination within the depletion region. Okay, so how do we model that? Well, recombination, Shockley-Holdridge recombination, we had derived this long, we had not derived, we had stated this expression that recombination is NP minus Ni squared, tau NP plus Ni here, and N plus Ni here, Et. So we said recombination takes place through, if I have EC and I have EV, recombination takes place through a defect level, ET. Electrons will fall here, hole will fall here, and they recombine. So ET, a trap level or a defect level, plays the recombination. That's how recombination occurs in silicon. Shockley-Holdridge recombination through a defect. ET is the position of the that recombination center with respect to the middle of the gap. Okay, ET could be somewhere higher up, it could be somewhere lower up. So ET is being measured with respect to the middle of the gap here. So as a simplification, what we have taken is a recombination center right in the middle. So ET has been taken right in the middle, which means ET equal to 0. ET we have put as 0. Okay, so this ET measured from middle. Measured from middle, and so we have taken this value as 0, mainly because the recombination primarily takes place through defect levels which are in the middle. Why? Because you can see very clearly, if I have a defect level ET which is close to EC, what would happen if I have a defect level which is close to EC? Then ET is large, and exponent ET will become, by KT becomes very large, R will become very small. Similarly, if you have a defect level very close to EV, this term becomes very large. And again, you find that recombination is very small. So you could have a defect level close to the conduction band, doesn't do much of recombination. You could have a defect level close to the valence band, doesn't contribute much to recombination. A defect level which is in the middle is the best recombination center. And that's why we are putting ET equal to 0 here. So once you put ET equal to 0 here, and for simplicity, tau n equal to tau p equal to tau. So what happens is recombination is Pn minus Ni square n plus p plus 2Ni 1 over tau. That's the recombination rate inside the depletion region we are talking about. It goes as here. So if you look at this term here, tau is a constant, n plus p, Pn minus Ni square. The recombination is, of course, total recombination current is Q times to add up the total recombination rate. We know inside the depletion region, Np is Ni square exponent QV by KT. So Jr is going to be, if I take Np minus Ni square, so we take this here, plug it here, so we get Q by tau Ni square exponent QV by KT. We get 1 by P plus N plus 2Ni, integrated from minus xp to xn. So the whole issue is, these terms are of course independent, they're outside the integral, this is outside the integral also. So the whole thing is, how does this 1 plus P plus N plus 2Ni, how does it go? So note that this is how P is going, and this is how N is going. So where do you think you will get most of the contribution to this integral? If you look at this region, somewhere here, what happens in this region? P is very large, and if P is very large, this term is very small. If you look at this region, N is very large, so again this term is small. This is at the center where you find P and N are the minimum. And so if I were to plot this function P plus N plus 2Ni, most of the contribution will come from this center. It's actually, note that P and N are varying very sharply. Very, very sharply, because you have concentration of 10 to the power 17 here, and you have a concentration of maybe 10 to the power 11 or 12 or 13 here. So very, very sharp variation is there. So this curve 1 plus P plus 2 plus Ni is a very sharp function, basically at the close to the middle here. It is this kind of function, recombination. All the recombination is coming here. So recombination peak, we are saying, if we look at this, will occur where P equal to, so it will not, maximum recombination will not occur where P is high. It will not occur where N is high. And one can show maximum will occur where both P and N are equal. And P and N are equal to N equal to P equal to Ni exponent QV by 2 kT. Because P into N is always Ni square exponent QV by kT. So where P and N are equal, both of them are equal to Ni exponent QV by 2 kT. And this recombination occurs in a very narrow region. So what we are saying is now, if you follow the argument, R max is equal to N equal to P Ni exponent QV by kT. And so what we are saying is, if you take this integral, there is a sharp peak and it's varying. We don't know how exactly it's varying. I mean, it's more complicated. So what we are saying is this whole function will be equal to 1 by, note that this Ni we can neglect, because this is Ni exponent QV by 2 kT. So this 2 Ni we can neglect here. It's much less than these terms here. So we can approximate it as 1 by 2 Ni exponent QV by kT by some effective width. Right? This is a sharply varying function. We don't know what it is, but some effective width which can be calculated. So then some effective width here. So then it turns out that we can write this Q by tau Ni square, and this integral we are writing as 1 over 2 Ni exponent QV by 2 kT into some effective width here. And so we get a recombination current which is Qni by 2 tau W effective exponent by QV by 2 kT. Approximate expression for this. This we are not going, it requires some more effort to calculate and show that what is this effective width here. Okay. So what is the argument? Maximum recombination will occur where P and N are the same, because of this term here, P plus N plus, forget about 2 Ni here. And so we are taking that maximum recombination rate, and we are saying, well, some maximum recombination rate multiplied by some effective width. Right? And effective width, more calculation shows it goes like this here. So this is our model for, so the total current is, it's not just this current that you just derived, but a recombination current which is Qni by 2 tau pi by kT Qf now exponent QV by 2 kT. Yes?
Could you really neglect that 2 Ni, because when P and N are both equal, it's both are of the order of Ni.
Both are equal to Ni exponent QV by 2 kT.
This exponent term is.
Yeah, but if I'm applying QV, let's say 0.4 or 0.5, this N and P are much, much larger than 2 Ni. We are talking about Ni into exponent QV by 2 kT. So you apply even 0.2 volt. So, right? So Ni into exponent 0.1 by kT is much larger than this one here. So we can forget about this term here. Okay? I'm talking about forward bias. If I were to talk about reverse bias, then everything will change. Okay? In reverse bias, the opposite would hold. P and N will become, if this were reverse bias, this would become negligible, and then this will become the dominant term, 2Ni. Okay? So in reverse bias, we are talking about forward bias here. So total current is this ideal diode equation that we derived, plus a recombination current which is Qni by 2 tau exponent QV by 2 kT. So what you find is PN junction has two terms in it, an ideal equation that we derived and a QV by 2 kT term here, which is the recombination current. So if I were to plug in these values, Qni by 2 tau, pi by 2 kT, F naught, all those, F naught is the field in the middle. If I were to plug it, this is what I would get. 1.75 into 10 power minus 11 QV by KT, 1.3 into 10 power minus 8 exponent QV by 2 KT. This is a more exact expression for current in a PN junction. For the same set of everything is given to you, you just have to plug in and you get these values here. So at 0.6, please note at 0.6, if I put here, at 0.6, the first term is 0.185, the second term is 0.0013. Negligible. recombination current in the junction. That's why probably you've never heard of people talking about recombination inside the depletion region. Nobody talks about it. Why? Because at around 0.6, 0.65, this term, just look at it here, negligible. But if I change the calculation at 0.3, look at the first term, 1.8 micron, second term, 2.57 micron. So at lower bias, the two are becoming comparable. And if I go even lower bias, this term will begin to dominate. So the current is this particular one, the 2 kT term. In fact, many of the diodes that you will take in the lab, say a diode which has been designed for rectification for your power supply, 220 volt power supply, right? So the diode, and it has to carry amperes of current. So if it has to carry amperes of current, so it's a pretty large diode, area is pretty large. And if you take the diode which has been designed for 1 amperes or 5 amperes kind of a current, and you operate it at 1 milliampere, if you operate it at very low current, right? So what happens is a diode which has been designed for 1 ampere and you're operating it at very low currents, so it starts to go into this particular mode. And you will, if you measure, you will find, well, you're not getting a 1 kT here. See, this one you can call it as 1 kT. 1 kT, and this one is 2 kT. So you don't get a 1 kT current. In many of the silicon diodes, if you measure, you don't get it. And in fact, many times you get a combination of this. So if you were to approximate this by a single equation, J equal to Js e to the power QV, then I cannot write 1 and I cannot write 2. So what I do is I write n kT minus 1. And n is something that you need to evaluate. So according to this, at higher bias, what would be the value of n? 1. At lower bias, 2. In between is going from 2 to 1. So in a PN junction diode, depending on the voltage you are, you may measure an this is called ideality factor. You may measure n equal to 1.8. You may measure 1.7. You may measure 1.5, 1.4. You could measure any of that, anything between 1 and 2. Yes.
But sir, at higher voltage, still that graph are showing some deviation.
Oh, that is a different part. We have not gone to that high voltage. We are saying it's still low level injection approximation. So here, this is a case of going from very low to sort of medium voltage. And we are ending up with this between 1 and 2 here. All right, so this is an important current that we forget when we are at higher bias, but this is important. These are also important. Imagine that if you take a solar cell and you use a solar cell under low light intensity. So solar cell under low light intensity, this is what would dominate. So at various places you find you need this ideality factor 2. At various places this becomes important, and the 2 you can see. Why is this important at low bias? Look at the pre-factor here. Pre-factor is several orders of magnitude larger than pre-factor here. So at low voltages, this becomes important, but as voltage keeps on increasing, this term doesn't increase as fast as this term. QV by KT increases faster than this particular term. So pretty soon what happens is this term overtakes this particular one and becomes much larger than this. And then you need to consider only this here. Okay. So this is, if you were to write J equal to Js 1 over n, so you could take J equal to Js exponent QV by nkt. From here you can derive 1 over n is KT by Q dl and J by dV. And if you take this equation, you can derive, what would be the ideality factor. There's a KT term here, there's a 2 KT term here, and if it's a simple derivative and simplification, you can get this here. All right. Okay. Let me before I come to this, in the remaining time, let's, I'll come back to this in a minute. Not reverse current. Okay, let's for a moment let's look at the reverse current. We have a quiz on Friday. We need one extra lecture tomorrow. Thursday 3 to 3:15. I guess people have class. 3:15 can we start? 3:15 to 4 or 4:50. One last to wrap up the PN junction. Okay. So reverse current, if you look at J equal to J exponent QV by KT minus 1. And if I apply this equation to reverse bias here, if I put QV by KT, reverse bias here, I get this current here. V as negative, I get this current here. And this is the current that you hear of, we call it as the reverse saturation current and all that. But this current, there are problems because you know that this equation has problems. Why? Because you have neglected recombination. Now, in forward bias, the whole issue is with recombination. In reverse bias, the whole issue is with generation. It's just the opposite. I want to show you that. So in forward bias, you're injecting carriers and it recombines and all of that. In reverse bias, the issue is one of generation. So see what happens here. Delta Pxn. What is the electron excess hole density here? So we've used this equation, Ni square over Nd exponent QV by KT minus 1. Okay? That equation, if you recall, only required us to assume that the electron quasi-Fermi level and hole quasi-Fermi levels were constant. Now, in reverse bias, the current is so small that the quasi-Fermi levels are constant anyway. Okay, so there's no problem with that. So these equations are valid whether you take forward bias or reverse bias. So if I apply reverse bias, QV by KT minus 1, delta Pxn turns out to be minus Ni square over Nd. Delta Nxp turns out to be minus Ni square over Na. What does it really mean? What is the actual electron density at this particular point then? Or hole density at this particular point? At equilibrium, how much do you have? Ni square over Nd. Delta Pxn is how much? Minus Ni square over Nd. So what is the net hole density is predicting here? 0. Negligible. Right? This is what is happening now. If you look at delta Pxn is here. Negative. Minus Ni square over Nd. What is delta Px at far away from the junction? 0. Far away from the junction, 0. So this is what is happening here. It goes like this. And this is going like this. Just the opposite of earlier we had going here. And we had going excess. We had excess here, excess carriers. And we don't have excess carriers. We actually have much less than here. So what is happening now? At this edge, you have carriers which are very small. Extremely small, right? Number of carriers, so we just said number of carriers here is practically 0. What is the number of carriers here? Far away? Ni square over Nd. So what is going to happen? What's going to happen? The carrier will diffuse. Now diffusion is like this. This is higher now. In the bulk is higher. At the edge is 0. So the carriers are diffusing here. Similarly, here you have Ni square over Na. And here, right here is almost 0. So they're diffusing. Minority carriers are, so holes are, note that this is holes. Holes are diffusing here. And they're diffusing. Once the hole comes in here, what is the field it sees? Positive. So it is swept by the field and then it comes into that particular region. Similarly, the electrons are diffusing like this. So it's still a diffusion current. When I talk about this, when you look at this current here, dP by Lp Ni square over Nd. Ni square over Nd is what? Ni square over Nd here, right? dP by Lp is what? Diffusion rate. Because how do you write J? J is Q dP del P by del X. So this is Ni square over Nd is here. And dP by dx, this term is dP by Lp, is diffusing from here. And is diffusing from here. So this is what is happening at this particular point here. Now as it is diffusing, what is happening to it? As it is diffusing, now remember, if you look at in the forward bias, as it is diffusing, what was happening? Why is it exponentially decreasing? It is recombining. It is recombining and diffusing. Now, as this is diffusing, what is happening? It's not recombination. As it's diffusing, then what is happening? generation. Just the opposite. It's not recombination anymore, it's generation. Because look at this term. Shockley-Hallreed, when I write Pn minus Ni square, and we wrote N plus and all that we wrote here, right? In equilibrium, Shockley-Hallreid Pn is equal to Ni square, 0. When I have Pn as larger than Ni square, then what do I have? Net recombination. When I have Pn which is less than Ni square, then what do I have? Generation. I have generation occurring. So this is what is happening in this region. If you look at this region, what is P into N here? Is less than Ni square. In all this region, P and N is less than Ni square here. Pn is less than Ni square. In all this region here, I have generation occurring. And I have generation occurring here. Okay? And so that is why you have, otherwise why would you have LP? LP has both diffusion constant. Remember, LP has square root dp tau p. Why would tau p come into picture then? Now, so earlier it was diffusion and recombination. Now you have diffusion and generation. So recombination was delta p by tau p. Generation is also like that. Generation also we can write in this particular form here. So anyway, so this is what is happening here. Reverse current is due to thermal generation and diffusion. That is what is happening. Thermal generation and diffusion here. So this was the expression. Note that complicated expression here. We put Et equal to 0, tau n equal to tau p equal to tau. So we write R equal to Pn minus Ni square n plus p plus 2Ni tau. So this is everywhere. Pn is less than Ni square. So we have generation now. R equal to minus G. And if I go inside the depletion region, Pn, so Pn is much less than Ni square, so Pn you neglect. And inside the depletion region, N and P are also much less. But for the moment, if you look at this region here, in this region, so Pn is much smaller than Ni, P is negligible, N is equal to Nd, so you get R equal to minus Ni square over Nd 1 over tau. So you get, this is the net generation rate in this particular region here. G equal to Ni square over Nd 1 over tau here. In this region here, this is the generation rate that you get here. Okay, so what we are trying to show is the following. This expression, so if you look at, so what we are saying is, look at this region here. And in this region, you could write generation rate as Ni square over Nd by 1 over tau. That's the generation rate by using this expression here. R equal to Pn minus Ni square n plus p plus 2Ni. Pn is much less than Ni square, and both P and N are much less than Ni. So we can neglect this, and so we end up with, we can N, not P and N. P is much less than Ni here, so we can neglect P, and N is equal to Nd, so that's why we end up with a generation rate Ni square over Nd over 1 over tau. So in this entire region, we have a net generation occurring here. And look at this particular part. If I take a region equal to Lp, and I multiply the generation rate with Lp. So I can write this as Jpn as Qni square over 1 over tau into Lp. That's the net generation rate multiplied by Lp, and I get this particular term here. So you remember the expression for reverse current that we were getting was Q Ni square over Nd dp by Lp, reverse saturation current, plus Qni square over Na dn by Ln. So what I'm giving you is an interpretation of what this is. What we are saying is, if you look at generation rate here, this is equal to Ni square over Nd 1 over tau. And if you take a region of length Lp and you multiply it together, total generation rate multiplied by Lp, you get this particular term. Q dp, this first term here. So in a way, what is happening is that you have all these generation occurring. You have electron hole pairs which are generating, and these holes are now going in this region here. Generation is supplying the current. It's not injection anymore, it's generation of carriers. Because minority carriers are flowing from N to P. What is the source of minority carriers? You must ask. The source of minority carriers is thermal generation. And so carriers are getting generated here and they're flowing into this region here. Similarly, carriers will be electron hole pairs are generating here and the electrons are flowing here. So it's a generation process which is supplying the current here. So in that sense, then you will say, well, you are looking at generation here and you're looking at generation here. What about generation within the depletion region? And it turns out that generation within the depletion region is the most significant term. Okay. Now how? Okay. So see the argument here. G is equal to, and what is it? This is the generation rate here. Here. This is the generation rate here. And so what we are saying is total generation current in the two cases here, and total generation current in two cases, you add up, this is what you get. So although we derived everything from forward bias consideration, this reverse saturation current that you get here is because of generation here and generation here. But now you think about it. So let's look at electron current. So we are saying electron hole pair are generated here, right? Okay, so the electron current comes here. But aren't electron hole pairs generated here? They will be generated here also. So what will happen to those electron hole pairs? That electron will also come out here along with it. So what is the total electron current? Total electron current is the ones that is generated here plus the one which is generated here. They add up. Similarly, the holes which go here, the holes come here, but electron hole pairs are generated here. This hole also will come here. So together they will come out. So what I need to do is, so far what I said was this is generation outside depletion region. I need to add that generation inside the depletion region. And it is for that reason, this I will do in the tomorrow's lecture. It is for this reason now you see why when you go in the lab and you measure, so you say J equal to Js e to the power QV by KT minus 1. And you measure Js, right? But first of all, remember the issue is more complicated. So you select a region and you measure Js. And you call it the reverse saturation current, right? You call it the reverse saturation. What is this Js? Js is this first term. Js is this first term. You measure forward bias and you fit the curve and you calculate Js. Js is this first term. But then you go ahead and measure the reverse saturation current actually of a PN junction. And you find the reverse saturation current is not equal to this. Why? Because we will see in tomorrow's lecture that this term is much larger than the first term. The second term, the generation inside the depletion region is much higher than generation outside the depletion region. This is a very important point. So what happens is when you actually take a PN junction and reverse bias, you will measure this current. But from forward bias, you are getting this current. That's why the reverse saturation current is not the reverse saturation current. What you have been calling J equal to Js exponent QV by KT is not the reverse saturation current. It's only Js is only a fitting part, Js, of a particular part of the characteristics. And you're missing this particular part here, the second part here. So that's the point that we need to see, that why is this second term so much larger than the first term, even though the depletion region is so narrow, right? Depletion region is so narrow. Outside, remember LP is what? LP is like 15 micron, 10 micron, is very thick. Depletion region is very narrow. But what happens is generation rate is very, very high in the depletion region. And so even though it's very narrow, the second term is very significant. and the reverse current of a PN junction diode arises from the second term and not the first term. Okay, all right, so let's stop here.